Well, let's get started. So today we still have like two problems. Let's take a look at the first problem. We have A and B. Oops, this is like B. And then let's talk about the 1A. So the question is asking given the graph G, and then also a subset of edges. And if we run the algorithm like Cusco, by the way, how do you guys pronounce this? Cusco or Crusco? Cusco. Okay, yeah. So like if we run the algorithm Cusco based on this subset of E, what will happen? Eventually, probably because like we don't have any cycle in this E, right? E, like E prime. So if we run the algorithm, we still can get a tree. Is that going to be the same as the tree we run Cusco algorithm from scratch, or it will be different? Yeah, so question is like, if we start from like different initial stage, what will happen? Any idea? Like anyone saying that, okay, they will be the same? They'll be the same? Or they'll be different? Like anyone feels like it will be different? Okay, let's take a look at the example. So this is the example, like we have the graph like this, right? And then this is case one, and then this is case two. So if we have the E prime, it's going to be like this. And then we run the crystal algorithm, right? So we choose the smallest, this one, right? So that would be like, well, let me do things. We just do things here. So we run the algorithm on this graph, right? And then we choose the smallest one. That's going to be this one, right? And then we do the union, that kind of things, and then we put this into the set. And then we choose the second smallest. Going to be 2, right? And then 3. So that's the result if we run like Cusco from case 1. How about case 2? Initially we still have this one, right? But instead, we don't have this one, we have this one. So what's the smallest right now? Those two, right? And then we can do something like this, this. So if we start from different subset of edges, even though this subset of edges doesn't contain any cycle, we'll probably will get like different result, right? And then by the eye browsing, which one is the true minimum spanning tree? This one, right? Why?
Because well, that one uses the edge with weight 3 instead of with weight 4.
That's true. That's true. We have 4 here. So this one is not the minimum spanning tree. So we know that even though E doesn't contain cycle, it's not guaranteed that in a starting point, this one is part of MST, right? Do you guys still remember the optimal substructure? Like we assume in Cusco algorithm, we have A set, right? And then we keep adding edges to the set A, and then eventually this set is going to be the minimum spanning tree, right? And but we assume that over iterations, this set is always part of MST, right? But if we start from like this point, it just violates the assumptions, right? Because initially we have something which is not part of MST. So in this case, they're different. But do you guys think that we have some certain condition we can make sure that eventually they are going to have in the same spanning tree? Yeah.
You don't include the largest edge of the cycle.
Yeah. Basically, that's a necessary condition. So it's like if none of the edges contains a cycle, also let me just write down statement. Okay, if none of the edges in E prime is the largest edge of some cycle. In G, we can make sure that E prime must be a part of MST. If that, we can make sure E prime must be a part of MST. So this one like looks very straightforward, right? Like if you look at this example first, and then you feel like, okay, this one is the largest way. So if we don't include this one, it makes sense, right? But if we really want to have this statement, we want to have we want to make sure it's right. So in the best case, we want to prove that mathematically, right?
Yeah, I'm not sure. Is that the cycle property? The one you just wrote that there?
Yeah.
Is that a cycle property?
You mean the
Yeah.
if condition?
Uh-huh.
The cycle property is like you can say that we use cycle property to have this statement, right? Like the cycle property is like the largest way in the cycle cannot be in the MST, right? So yeah, so right now, if you want to prove this statement, do you guys have any idea how to prove that? Yeah, we can use cycle property, right? For example, let's say we have the edge. We have like E, right? And then E must be E prime. That must be something like let me just write down here. E prime must be something like this. And then we say that this is the E prime doesn't contain any cycle, right? So this is not a cycle. And then at the same time, so we can prove by that contradiction. So if this E prime is not part of MST, it's not part of MST. So we have like U, D, right? And then this is like E prime. And then we assume like this is part of MST. So if this is not true, we hope that this is not true. So that's we can prove that by this logic. Any question? Clear? Okay. So that's E prime, and then we assume this is not part of MST. But we know for MST, the tree has to be traversing all of the nodes, right? So if this is not part of MST, we definitely still have another path to connect U and V, right? Because U and V does not, it's not connected by this path. We say that we want to have like MST, right? That MST can connect U and V, but that MST does not contain this this path, right? So we definitely have to have another path to connect the UV. Question? So this part, let's just assume this part is going to be another path, and this part is going to be part of MST. T is MST. Okay. Okay. And then we can prove that by the cycle property, the contradiction. Any ideas?
That's the additional condition that we need to have the Driscoll. Alpha, the one she wrote out there.
Where? Like here?
Yeah, no, the dot, not of the edge, the E prime is largest edge of some cycle. That's the additional condition that we need to add to the.
Yeah. So by proving by contradiction, right now we have the cycle here, right? So we know that according to like cycle property, we know that the largest edge is not going to be part of MST, right? It's not going to be the part of MST. So the largest edge is not going to be here. Make sense?
Yes.
They must be here, right? They must be here. But we already said that this one doesn't contain any largest edge in here. So that's a contradiction. Make sense?
So,
Yeah.
On what grounds we can say this? None of the edges in E dash is the largest edge of some cycle. Like how we get to that?
E prime.
Yeah. Like none of the edges in E prime are the largest edges of some cycles. How can we take that? Like, what is the reason of assuming this? Like,
oh, okay. So, yeah, for people coming later, let me just quickly explain what I'm talking about. So initially we have E prime, right? E prime is a subset of the edges, right? And then we start rounding Kruskal algorithm from E prime, right? And then probably we can get the MST, probably we cannot.
correct.
Right? Because sometimes if we're, let's look at this example. If we run from like this kind of E prime, we can get the MST. But for this one, we cannot. Why? Because this E prime already contains the largest edges in this cycle, right? So in the beginning, this E prime contains something which is not part of MST. So it's like already run in the beginning. So if we run the algorithm from that initialization, like initial stage, we'll get the wrong result, right? So my question is like, that doesn't guarantee to get the optimal result, MST, right? But if we can add any condition on that, can we have the MST in the end? So that's the condition.
Okay.
So if E doesn't contain any cycle, also none of the edges in E is not the largest edge of some cycle in G. If we have those two conditions, we can make sure that E must be a part of MST, right? But that's just like straightforward thinking. So I was saying that, how do I prove that by contradiction? So by proving this, we can say, okay, we have like E prime like this, right? And we know MST has to connect all of the nodes, right? So like a UV must be connected. And then we prove that by contradiction, saying that, okay, this part is E prime, this E prime is not a part of MST, right? So if that's not the part of MST, we must connect those two nodes by another path, right? That's the other path. And then this another path is like part of MST, right? Because this is not part of MST. So this part is like part of MST. And then right now we have cycle. So we can apply the cycle property, which says that in this cycle, the largest array is not part of MST. So we know this is like MST, and then by applying that, the only result we can get is like largest array must be here, right? But that's already contradiction.
So when we say that there is another path connecting U and V, which is part of MST,
Yeah.
there can be a third path also connecting U and V, and that could be part of MST. And so there could be three paths. One is U to V that is there in E dash, E prime, which is larger, which is not the smallest one. So which means that there is one smaller one path that is there, but there could be the third path also, which could not be smaller and which could not lie in MST. That can that happen?
I think we don't need to really talk about the weight right now. We just need to like think of like if E prime is not part of MST, the MST must connect those two by the other way.
Any other path.
Any other path like this, right?
Okay.
And then in that case, we have cycle, right?
Correct, makes sense.
And then by the cycle property, the largest edge cannot be here.
Correct.
Must be here.
Okay.
That's the contradiction.
Okay.
Right. So if this is like not part of the MST, we get the contradiction. So if that's not right, that's not right. So basically this statement is right. Make sense?
Makes sense.
Yeah. So yeah, that's the result. But let me just ask you guys another question. So if we have E prime, and then E prime doesn't contain any cycle, and then E prime doesn't contain the largest edges in the graph. If we run the Kruskal algorithm from E prime, and then we run the Kruskal algorithm from scratch, does that guarantee the MST is going to be the same?
No.
Why?
Because there can be some vertex which is not being connected from the edges in E prime.
Not precisely correct. Yeah.
Maybe like the edges in E prime is not small enough to be in MST.
We know that by this condition, we know E prime must be part of MST. Must be, right?
Okay.
There might be more than one possible MST.
Yeah, that's right. They contain like E prime, right? But at the end, they probably have like different edges. Like they are as large as like they're equally large, and then you have like a multiple MST. But they definitely contain E prime. Yeah.
Is it because the weights of the edges are not unique?
Yeah. So you can imagine like if we have something like here, like this, right? We have like MST like this way or this way. We have like two possibilities, right? So if you run like Kruskal from E prime, definitely if you start from like this one, definitely you will get the MST. But probably at the end, we have like multiple MST. So that doesn't guarantee we have the same MST. But we know that E prime must be part of MST. This statement is right. But we just cannot make sure they have identical MST. Yeah. So yeah, that's the first part. And then let's take a look at the second one. The second one, okay, let me just erase this part. So I think that like if you guys have some statement or some like thoughts in your mind, you can try to prove that by like cycle property or cut property, to prove by contradiction to see that if the statement is correct or not. Yeah.
Yeah, so the question says that, how can we update the algorithm? So for that, is it sufficient if we just add the condition, the initial condition that E dash does not have a cycle? And, somehow also satisfies the cycle property, so basically we're adding these two conditions and then we run Crystal as it is, so is that the updation to the algorithm that you're making?
Yeah. If the goal is to get the MST, that's the way. But if the goal is to get the identical MST, we must add another condition to make sure they are only unique MST at the end. Making sense? Okay. So, okay, let's talk about the second one. Okay, the second one is that we have graph, right? And then this graph contains negative edges. And an algorithm that can return a minimum spanning tree when given a graph with only positive edges. So we have the graph that possibly contains negative edges, but we want to have, we only have the algorithm which returns the MST when all of the edges are positive. So any idea to deal with that? But before getting into this question, let me just ask you, can we run Kruskal algorithm for negative edges?
Thanks.
Anyone? Yes, we can. No? Anyone say no? No? I was gonna say, I don't know. What?
I think we can,
Why?
you like from Crystal algorithm, run from the smallest edge, right?
Yeah.
Because negative number can be still. Like you just adding smaller numbers to a big one step by step. You do basically the same thing. Like I don't think there's any constraint
Yeah.
about not using negative edge.
Yeah.
I think, Richard Kruskal algorithm doesn't actually like add an edge to like a cumulative total, right?
Mm-hmm.
So therefore, because it doesn't add an edge to the cumulative total, the reason why negative edges kind of screw up things in the first place is because they make the total or cumulative path smaller than it was before.
You were saying like if we compare that with shortest path algorithm.
Yeah, like with the shortest path.
Mhm.
That's the reason why negative edges didn't work in shortest path. So if there's no so if we don't have a cumulative total variable, then maybe it won't be a problem.
Yeah, both sound right, and then the answer is right. Like Kruskal doesn't run into that trouble. But if we explain that, like if we look at the algorithm, I will talk about this thing from like a 3D perspective. So I'll talk about that later. But you guys are right. Like if we run Kruskal algorithm, that's basically that can solve this graph. But if we only have the algorithm that can only give us like the result when all of the edges are positive, what we're gonna do?
Can we just like take the maximum negative edge and then like just add +1 of that weight, and what I mean is like if I have like a -7, which is like the maximum negative weight, I'm just adding +8 to all the edges. So like 1, and the others are like all positive. Then it's just
I think we add all the negative, like we sort the negative edges from smallest to largest. And then we add all of them to the minimum positive MST. And whenever it creates a cycle, we remove the largest positive edge.
Okay. A lot of different thoughts.
Or we could just remove all the or all the negative edges from the queue in the first place.
Removing them,
Yeah.
and then,
Does the MST, is it even allowed to have negative edges in it?
yeah, yeah,
Oh, okay.
right, like. Yeah, so. Yeah, so like the simplest way is like, just like what you just mentioned, right? We add the maximum negative value, absolute value, and then we try to get the MST, because that's still like the smallest edges to connect all of the nodes. Making sense? Does that make sense? Like if we have like a, at the end, we just want to choose like that many edges to connect nodes, all of the nodes, right? And then make sure the weight is like the smallest. So if you just add some positive number to shift from like, to make sure that all of the edges are positive, we still have the smallest like total weight. Does that make sense? So that's pretty straightforward. And then, but there are so many like things we can discuss in this problem. So let's look at the shortest path and the MST first. So in this problem, in the problem itself, if we don't talk about the algorithm, the problem itself, can we have negative edges in the graph? Because like the problem itself, like we also talk about like optimal substructure, right? Right, we talk about because we want to use greedy algorithm. So that's the reason we have optimal substructure in those problems, right? So in those problems, if we look at the optimal substructure itself, can we have negative edges in those two problems? For example, the shortest path algorithm, then the optimal substructure is going to be like this is like B. We tried out all of the right. Like if we tried out all of the neighbor, and then this one has to be the shortest path, and then we just pick the minimum, and then we have the original problem and the sub problems. That's the optimal substructure. For the problem, we can still solve the original question, which is shortest path. So if you look at this like optimal substructure, does like a negative value change anything? No. Right? So as long as like, I think like as long as we don't contain like negative cycle, because in negative cycle, we don't have the solution for shortest path, right? We just keep running, traversing the same cycle. But if we don't have that thing, the problem itself can contain negative weight. So that's the reason if you run Bellman-Ford algorithm, that's fine, right? Because Bellman-Ford algorithm is a dynamic programming algorithm, which is based on this optimal substructure. So if this is no problem, this is like, okay, we don't have problem with that. We can contain negative edges. MST is the same thing, right? We use like cut property to choose the minimum one, across the cut, right? Like across the cut, we just choose the smallest to connect all of the nodes. So if we only look at the problem itself, we don't have any problem with negative edges. But if we look at the algorithm, why digestion doesn't work, and then Cusco works? Because for a digestion algorithm, we have Q, right? So we have something in Q. And then we have something pop out from Q, right? We have initially we have the force, and then we pop out source, and then we start updating the neighbors, right? So every time if we pop up something from the priority queue, that means that those edges are already optimal. The shortest path we already know, right? And then we're updating the things in queue. So let's say we have like A, B, C, D, 4 different nodes. So if we update A, B, C, D in the queue, and then right now, if A is the minimum, it's like distance I, minimum distance I, A, B, C, D. If A right now is the smallest in the priority queue, we will pop it out, and then it will join the optimal set, right? But why this is optimal? Why this is optimal? Because we know that from the optimal to A, we already know there's a path from like S to A, right? That's here. And then the distance is like this, right? So if we want to go from S to A without going those things, this is already the minimum. And also, if we have another way, from S to B, from S to C to A, or from S to C to A, from S to D to A, we know they are going to be larger than from S to A, right? Why?
That would be only in the case that all those edges are positively weighted.
Yes, right? Because we know already like, let's say SA is smallest among SD, 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 right? So if we go from S to B and then go from B to A, no matter what kind of edges we are going to cross, it's going to increase the distance, right? So if you look at the algorithm, you'll see why we cannot have negative edges, because the negative edge will break the rule here, right? So we cannot make sure every time we pop out, that's the optimal. Probably that's still not the optimal, and then we still have to keep updating that. In that case, in the digestion algorithm, that doesn't work, because once we pop out, we don't update the distance anymore, right? We just update the things in priority queue. So that's the reason for digestion algorithm, we cannot have shortest path. But for Cusco algorithm, that's fine, right? We can still have negative edges. But can we use the things you just mentioned for shortest path? Let's say we run the shortest, we have like negative edges in a graph, and then we don't want to use Bellman 4, and we feel like, okay, I don't know Bellman 4, I just want to use digestion, and then we add all of the edges for like positive number to make sure that all of the edges are going to be non-negative, and then we run digestion, and then we get the result. Is that going to be the same as like shortest path from digestion?
Pretty sure we had a question in our homework where we had to find an alternative for the shortest path that would count for negative edges, right? So I think we do. I guess the general question, is there an algorithm that gives the shortest path with negative edges? Sure.
Yeah, I mean, like obviously like Bellman 4, right? So we can use that. But I mean, can we do that? Do the same thing? And then if
To me, like what you just suggested, you mean like dice throw, but then you add an offset so that every
Yeah.
positive?
Yeah.
If you add everything by an equal amount, so that the lowest edge is now positive, I think it should be the same.
Should be the same?
Yeah.
Anyone say like it should be the same? Or same? Anyone is like, no, they're not. 1, okay, 1 versus 1. Anyone has no idea? Yeah.
Like if you're not like
if you have like a negative, it's poorly worded, but if you have a negative weight edge, like that takes away from the, between like A and B, that takes away the distance to get to B, so it's suddenly become shorter than if you were going through A. So like, that's the source, something like that. So I feel like if they're not negative, then you don't have that like decrease in overall distance.
So your answer is,
I feel like it wouldn't work.
you say it's no.
Yeah, I know.
Okay, yeah, I think like you are very close. Let's just give you the example and then there'll be more concrete. Okay, let's say like we have the source and the destination. If we go from like path one here, we have path one here. What's the total cost?
2.
2. And then if we go from here, what's the total cost? 1. So initially, you will choose this one, right? Because this one is smallest. But if we, let's say, oh, we contain some like negative edges here, so we add like 3. What will happen? This is like, okay, 0, 8, 6, 4, 0. You calculate it again. This is going to be 8. This is going to be 10. And oh, okay, choose this one. What will happen? You will choose the other path as the shortest path, right? Why?
Because like the other one has more edges, so when you add 3, that one becomes longer.
Yeah. So like that's the problem. Do we have this in MST? Why?
Turns out like the greedy approach is the optimal approach, but like in the shortest path, the greedy approach isn't necessarily optimal.
Yeah.
Because we're sorting the edges anyway, so even when we add individually, the sorted edges would still maintain the same one. So, and we pick the edges from the sorted list of edges.
Not you guys are like not really answer the question. So basically, if you see this this problem is like because the shortest path contains like this one contains like more edges. So if you add like the positive number to every edge, you will change the shortest path, right? But for MST, they have the same number of edges. That's going to be this one. So eventually, right, if you add the same number to every edges, that's fine. That change nothing. Let's just shift. You have an offset, but that doesn't change the MST. Make sense?
Yes.
Make sense? Yeah. So for this alternative short path, no. MST, yes. Yeah. So you can look up the problem itself to think about the negative edges cases, and then also think of that from like algorithm perspective or the alternative perspective. Yeah, so that's basically it for the question B. Oh, yeah, question B.
You want this one?
Ooh.